Welcome back to the third in our series of videos on conceptual modeling featuring the well-established entity relationship model and ER diagramming. This series of lectures is based upon a textbook by El-Masri and Navath, Fundamentals of Database Systems, 6th edition. In the previous video, we were introduced to the flow of steps or phases that we must go through in the development of the database, from the initial gathering of information to the development of the conceptual model with the end user to determine the data that needs to be captured and the needs of the database. This conceptual model is then transformed into an implementation data model in the logical design or data model mapping, and the result is the database schema in the implementation data model. The last step is the physical design phase, where all the internal storage structures, file organization, indexes, and so on are specified. In this video, we're going to continue our examination of the entity relationship model. The basic object that the ER model represents is an entity, which is a thing in the real world with an independent existence. An entity may be an object with a physical existence, such as a part or a house or a student, or it may be an object with a conceptual existence, such as a course or a class. There are several implicit relationships among the various entity types. For example, the attribute manager of department refers to an employee who manages the department. Each entity has attributes, the particular properties that describe it. For example, an employee entity may be described by the employee's name, age, address, salary, and job. A particular entity will have a value for each of its attributes. The attribute values that describe each entity become a major part of the stored data in the database. Composite attributes can be divided into smaller subparts, which represent more basic attributes with independent meanings. For example, the address attribute of the employee entity can be subdivided into street, address, city, state, and zip. Composite attributes are useful to model situations in which a user sometimes refers to the compositive attribute as a unit, but at other times refers specifically to its components. If the composite attribute is referenced only as a whole, there is no need to subdivide it into component attributes. Since in most databases there is no mechanism for defining composite attributes, the decision must be made at design time whether or not there is a need to create individual attributes for each of the components. Most attributes have a single value for a particular entity. Such attributes are called single-valued. Other attributes may have multiple values for an attribute. For example, one person may not have a college degree, another person may have one, and a third person may have 2 or more degrees. Therefore, different people can have different numbers of values for college degree attribute. Such attributes are called multi-valued. In some cases, 2 or more attribute values are related. For example, the age and the birth date attributes of a person. For a particular person entity, the value of age can be determined from today's date and the value of the person's birth date. The age attribute, therefore, is called a derived attribute and is said to be derivable from the birth date attribute, which is called a stored attribute. In some cases, a particular entity may not have an applicable value for an attribute. For example, a college degrees attribute only applies to people with college degrees. Not every person in the table may have a college degree. For such situations, a special value called null is created. A person with no college degree would have null for college degrees. Nulls can also be used if we do not know the value of an attribute for a particular entity. The meaning of the former type of null is not applicable, whereas the meaning of the latter is unknown. The unknown category of null can be further classified into two cases. The first case arises when it is known that the attribute value exists but is missing. The second case arises when it is not known whether the attribute value exists at all. Notice that in general, composite and multivalued attributes can be nested arbitrarily. We can represent arbitrary nesting by grouping components of a composite attributes between parentheses and separating the components with commas, and by displaying multivalued attributes between braces. Such attributes are called complex attributes. Those of you that have been studying SQL already have already discussed some of these issues in the context of developing the SQL programs. Bear in mind that in the conceptual phase of the development of a database, we're not bound by the constraints of any database system as such. We are in the design and idea development stages where we're defining these structures such as composite attributes and derived attributes without specifying how they're going to be implemented. Once we have completed this conceptual phase and we move to implement the design that was conceived in some database or other, it is at that time that the decisions will be made on how to develop these composite or multi-valued attributes. Well, that's enough for this video. We haven't even discussed a mystery word yet. We just finished talking about derived attributes, the age and birth date and so forth. So let's make derived attribute our mystery word for this video. Go ahead and submit the mystery word. Go out to check your knowledge on the material covered in this video, and when you're ready, come on back for the next video in the series on conceptual modeling using the ER diagram.